Hi everyone, nice to be here. I am Shirin Malihi, Marie Curie Fellowship from University of Cambridge. I present our paper on pole-shaped object extraction from LiDAR point clouds of roads. This issue presents an innovative and computationally efficient algorithm for the extraction of pole-shaped objects from mobile laser scanning point clouds. The methodology addresses the computational challenges associated with large-scale point cloud processing through a trajectory-based segmentation and ground point filtering. The algorithms include general flowchart, data preprocessing, extracting candidates, poles, clustering results, and conclusions. General diagram of the paper is presented here. The method has the advantage of relying solely on the 3D point clouds and trajectory data. The method's versatility is further demonstrated by its ability to handle data from multiple mobile laser scanning platforms and operate efficiently in both urban and suburban environments. This adaptability enhances the algorithm's robustness and broadens its applicability across diverse geographic locations and point cloud characteristics. It starts with pre-processing of the point cloud and segmentation and ground removal and noise removal of the point clouds. Afterwards, candidate of pole-shaped objects is detected, and geometric feature extraction will be done to extract the pole-like objects. After several filtering, the final pole objects are used and modeled for the rest of the research. The data was captured by a mobile laser scanning platform. You can see a typical mobile laser scanning platform, which equipped with a GPS antenna, IMU, and laser scanners on both sides. The data includes the urban region from USA with its high object density and reflective surfaces, which complicates the distinction of pole-shaped structures due to overlapping vertical objects and occlusion. The next one was from a suburban area in USA, while less dense still presents challenges with trees, power lines, and scattered buildings. And the third one was in a suburban area from China, which adds complexity due to geographical differences, sensor calibration variation, and environmental factors like vegetation and local infrastructure. Mobile laser scanning system leverages trajectory data to efficiently segment point cloud information by recording the vehicle's precise location throughout the scanning process. This trajectory data, which is inherently aligned with the point cloud coordinate system, allows for seamless segmentation of the scanned environment into uniform sections without requiring complex georeferencing. Just such as the picture you can see here, by dividing the trajectory into fixed length segments, the corresponding point cloud data is simultaneously partitioned into equivalent sections. After sectioning the point cloud, noise removal was done. You can see a huge number of noise points scattered here on top of the cluster of the points. We use a SOAR algorithm, which operates by calculating the mean distance from each point to its neighboring points within a specified radius. Next, we face with a huge amount of ground points, which actually we do not need them. We use closed simulation filter method to remove the ground points, and this algorithm offers an innovative approach to ground point removal in mobile mapping point clouds by addressing the critical challenges of data volume reduction for efficient processing and analysis. By simulating a close-like surface, it drapes over the point cloud and the algorithm mimics gravitational effects effectively, classifying points as ground or non-ground based on their position relative to this simulated surface. This method demonstrates remarkable versatility capable of handling diverse terrains, including both steep and flat areas, making it particularly valuable for large-scale point clouds. Firstly, it starts with inversion, train flip to simulate close falling inward. And then close simulation is done by a mesh with model as springs and mass points under gravity. Thirdly, collision detection is applied. Close conforms to inverted road surface. Final surface after inversion back is generated by close approximation road surfaces. And finally, segmentation, which classify road versus non-road based on point to close distance. Here you can see the output of this result of this method. The series of algorithms effectiveness hangs on the two key parameters, grid size and classification threshold. The grid size, which determines the resolution of the closed mesh, plays a crucial role in capturing train features accurately. By analyzing the surrounding neighborhood points, we aim to assign meaningful descriptors to each point. We know that power lines typically exhibit thin, lengthy, linear structures, while objects such as poles tend to have a long vertical shape. To distinguish between these types of objects, rule-based descriptors of linearity and verticality are employed. These two geometric features are particularly effective for characterizing pole. After pre-processing using these features, the candidate poles are detected, and afterward, using Euclidean distance clustering and height filtering, the pole-like objects are detected. You can see the verticality and the linearity features and the definition of the neighborhood and the thresholding which was done in this research. For three data sets, you can see the verticality in three different radiuses and density of the point and the amount of the verticality and how big, depending on the fact that how big they are depicted here in this picture by different colors. Basically, in three data sets, pole shape objects shows higher level of verticality, which are depicted with red, and also in linearity feature, pole shape and also power lines shows a high level of linearity for these features. However, verticality is not enough to actually distinguish between the pole shape and some other objects which are is connected to vegetation. To detect pole-shaped objects in a point cloud using an unsupervised approach, we employ DBSCAN. In this algorithm, each point is represented by a feature vector, which you can see here in this slide. The descriptors serve as indicator of whether a point is part of a pole-like object or not. The DBSCAN algorithm requires two parameters, the maximum distance and the minimum number of points. If the number of points within this neighborhood is greater or equal to minimum points, then the point is considered as a core point, which is a point around which a cluster can form. The parameters which was used in the research are listed here. The length of the segmentation by the trajectory data was 90 meters. SOR number of neighborhoods 10. The CSF grid size 31 centimeter. Neighborhood radius 90 centimeter. DBSCAN clustering parameters were half a meter and 10 points, and also ground clearance threshold half a meter. The results of the algorithm for the urban area of the West are displayed here. You can see the pole-shaped object among the vegetation and the road surface, which is actually this road access. It is somehow very well detected in the viewpoint of visual examination. The next one is belong to a suburban area. Pole shape are detected, however, some of them are among the buildings and vegetation coverage, which shows actually some conflicts in the viewpoint of detection of some of the pole-shaped objects. The next one is the next picture shows the suburban areas in China. You can see all of the pole-shaped objects could not be detected here, and the pole-shaped objects has a different shape. They have some actually overhangs, and it shows it implies some lack of efficiency in our algorithm. Performance metrics of the proposed algorithms are listed here. Precision of all the methods shows good results. Recall for the urban area shows the least percentage, and also F1 score. And in the viewpoint of time, the urban area needs the highest time of processing. The proposed approach leveraging trajectory-based segmentation and geometric descriptor, and it was designed to offer improved efficiency over existing techniques for pole-shaped object extraction from mobile laser scanning point clouds. Unlike voxel-based methods, which relies on computationally intensive grid construction and transformations, our approach uses trajectory data to segment point clouds directly, simplifying pre-processing and reducing computational overhead. It is particularly efficient in the viewpoint of real-time and resource-constrained applications, distinguishing our method from existing techniques that often trade off speed for additional data dependencies or processing step. While the proposed algorithm demonstrates robust performance across diverse datasets, achieving an average precision of 97% and recall of 96%, a small number of misclassified cases warrant critical discussion to understand limitations and guide further improvements. Notably, the algorithm missed two pole-shaped objects in the experimental evaluation. The low false negative rate, which is actually depend on the undetected points versus detected one, suggests that the algorithm remains highly effective for most practical purposes, such as infrastructure mapping near complete detection surfaces. In the picture, you can see a pole-shaped object near a tree. Actually, it depicts a case of occlusion. Occlusion by dense vegetation or overlapping infrastructure likely obscure the geometric signatures of these poles. In urban and suburban environments, poles are often situated near trees or cables, which can disrupt the continuity of point cloud data, reducing the effectiveness of linearity and verticality descriptors. Future enhancement could include adaptive neighborhood sizing based on local point density to better handle occlusions, or the integration of contextual features such as pole top equipment recognition to improve the detection of non-standard poles. Thank you so much for your consideration.